All right, so histograms are the picture version of what we just looked at. You're going to develop an ability to picture the distribution of data in a histogram or relative frequency histogram. You're going to examine a histogram and identify common distributions, i.e. uniform and normal. Okay, so what is a histogram? It's a graph of bars of equal width drawn adjacent to each other unless there are gaps in the data. On the horizontal scale, it represents classes of quantitative data, so that left-hand column, data values, and the vertical scale represents the frequencies. The heights correspond to the frequency values. So that sounds complicated, but in a picture I will show you. In SPSS, you're going to go to Analyze Descriptive Statistics Frequencies. Okay, you bring your variable over. Now you're going to click on Charts. When you get charts, you're going to come down here and you're going to select histogram. You can choose to put the normal curve on the histogram. You don't have to. Here in this demonstration, I didn't do it. And then you'll get this output. Now looking at that, I can see that we have roughly a normal distribution. We have a few modes here, but I would say that most of the data are kind of to the left, and we have a longer tail here. So I would call that a right skewed distribution, but it's subjective. What I say doesn't necessarily mean what has to go. I'm going to show you different types of positively and negatively skewed distributions. So in a positively skewed distribution, the scores tend to pile up on the left side of the distribution with the tail tapering off to the right. In a negatively skewed distribution, the scores tend to pile up on the right side and the tail points to the left. Okay, so what does that mean? All right, here's a skew. The thing that you have to remember, we all know what dogs and cats' tails look like. They're the skinny part, right? So you have to remember that the tail is the skinny part. It's the part that tapers off. It can taper off to the left. See how this part's skinnier than this part? So here's the tail, and when we're looking at the tail, we're interested in which way it's pointing. This is pointing to the left, therefore it is pointing to the negative side of the graph. We can call it a negative skew, or we can call it a left tail skew, or we just can call it a left skew. All right, it's because the long tail is on the negative side of the peak. Some people say it's skewed to the left. The long tail is on the left-hand side. Now this dark black line here with the arrow pointing to it called mean is the actual mean of this distribution. Notice it is to the left of the peak because these tails, these outliers, these few low numbers are pulling the mean that way. Okay, then this normal distribution is a symmetrical distribution. 50% on either side is perfectly symmetrical. You could fold that in half and then one side would lay directly over the other side. And the mean is exactly at the peak. So the positive skew is right skewed, skewed to the right. It's the same thing. Here's the tail. The skinny part is pointing to the positive side of the graph, pointing to the right. The mean is to the right of the hump. One way you can remember that is the mean dog chases his tail, right? So here's the tail and the mean is chasing the tail. It's just a little way to remember which way the mean is on, or which side of the hump the mean is on. All right, so we have three different types. We have negative skewed distributions, positive skewed distributions, and normal distributions. In the book, they mention normal quantile plots, but we're going to go into that at greater length in Chapter 6. But these are plots that are used to assess whether or not your data follow a normal distribution. In SPSS, they call it a QQ plot, and I'll show you how to make them. But right now, all you need to know is if the lines follow if your data points follow this line, you're more normal. If your data taper off to the right, then you're right skewed. If they were to taper off to the left, it would be left skewed. All right, graphs that enlighten and graphs that deceive. Graph data using dot plot, stem plot, time series graph, Pareto chart, pie chart, and frequency polygon. We're going to look at all of those. We're going to determine which graph is deceptive through the use of non-zero axis or pictograph that use an object of area or volume for one-dimensional data. Okay, that's in the textbook. I'm going to go just briefly through this because a lot of these we're not going to be using in the class. So, page 56 to 60 lists several different types of charts and graphs. Please review that. I'm just going to go through these really quickly. Dot plot displays the distribution of the data. Stem plot, which is also called a stem and leaf plot, gives you a quantitative display that shows the distribution and retains the original data, and it's presented in order. It's a little bit cool. You'll see that on the next slide. Time series graph shows trends over time. Bar graph, relative distribution of categorical data. Pareto chart shows relative distribution of categorical data in descending order. Pie chart shows distribution of categorical data in commonly used format. And then a frequency polygon is very similar to histograms but use line segments instead of bins. Okay, so here's a dot plot of calcium levels, right? You can kind of see the distribution. It's almost like a histogram. Stem and leaf plot. So here, this is the original data. Whatever count this is, there was a 44, a 46, a 47, a 49. So they put the tens here, or down here the hundreds, and then they give you the ones on this side. There were no 50s. Then 63, 64, 66, 268s. The interesting thing about this is if you were to flip it over counterclockwise one turn, you would see a similar distribution like this. So SPSS creates them very easily. You can use them or not. We will likely not use them in the class, but we can. You could play with that in SPSS. Time series graph just shows data over time. So here's the time, and then here are errors depending on whatever it is that this particular graph is measuring. This is a bar graph. Notice in a histogram, the bars touch unless there's missing data, but here it's categorical. So Europe and North America are two separate and distinct things. They are discrete. They can't be. You can't be Europe and North America at the same time. And so bar graph only is used for nominal or categorical data. Pareto chart's similar, right? We have the same thing, but it also uses the cumulative frequency here. And then when it gets to about 80%, people make different decisions based on their Pareto charts. Yeah, so you can read up on that. Pie chart is very, very familiar to us. We see these in the newspapers all the time. And then a frequency polygon, I could have easily put a histogram here, and at the middle of each of these bars, I know this isn't a histogram, but a bar like this would be this point. So this is essentially a histogram with the bars removed and replaced by a continuous line. You'll see that in the COVID-19 trends over the last few months. Okay, so ways that our graphs are used to deceive us. They can give us a non-zero vertical axis. Pictographs can be misleading. That means like the picture of the coffee cup in the textbook. Data that are one-dimensional are being represented as two-dimensional, which can be distorted. So when you double each side of a square, it actually increases by a factor of 4. When you double each side of a cube, it increases by a factor of 8. So it really distorts the data to take a two-dimensional thing and make it into three-dimensional when it really should just be two-dimensional. All right, in section 2.4, personally, I think they're getting a little ahead of themselves because we're going to talk about this much more in later chapters when we cover correlation and regression. But a scatter point, each one of these dots is a single individual, perhaps. Yes, it is. So if I were to take myself and measure my waist in circumference, I would get a measure here. And if I measured my arm circumference, I would get a measurement here. So each one of these dots represents one individual with two measurements. All right, we can see a clear trend, a positive upward trend for those data. Scatter plots and correlations. So a correlation exists between two variables when there is an association between them. So it's not unusual. If you have a very large waist, you're probably going to have a very large arm circumference. And if you have a tiny, tiny waist, you're probably going to have tiny, tiny arms as well. That's why this is a positive, strong correlation. So when two variables, when there's an association between them and you have a continuous measure, well, you can have any other kind of measure, but right now we're going to talk about continuous because that's what these data are. If you have two scores for one individual, for a group of individuals, you can make a scatter plot and look at the relationship. When this relationship is linear, the scatter roughly follows a straight line, which this one indeed does, right? I could draw a line pretty easily through the middle of there. It's a visual depiction of paired data, X and Y. X is the horizontal and Y is the vertical. But just because there's a relationship doesn't mean one caused the other. Just because you have a large circumference of your waist does not mean that you also will have a large circumference. It doesn't mean you're bound to have it because it causes it. It's just observational. You cannot imply causation for anything other than an experiment. If you want to say smoking or secondhand smoke causes cancer, we would have to do an experiment where we subjected people to secondhand smoke and then measure them over a long time and see if they develop lung cancer. Not necessarily an ethical thing to do. So we could do it also through a correlational study where we look at people who reported whether or not they were exposed and how long they were exposed to secondhand smoke, and then see if they later, if they also developed cancer. That's a retrospective study, but we can't do that. We can't say it caused it unless we did an experiment. Okay. So when we do that, when we do calculate a correlation coefficient, it's called R, Pearson's R. We'll talk more about this in chapter 10, but it's a measure of the strength of the relationship between X and Y. It ranges between -1 and 1, where the sign denotes direction and strength of the relationship is measured by the magnitude of the coefficient. The larger the number, the stronger the relationship. The smaller the number, the lower the relationship. Okay? If it's positive, it's going up and to the right. If it's negative, it's going down and to the left. But if I have a score of, or a correlation coefficient of -4 and a correlation coefficient of, negative 0.4 and a positive correlation of 0.2, so -4 is actually the stronger correlation coefficient. Even though it's negative, negative doesn't mean anything about the magnitude, it just tells us about the direction. So the number, the larger the number, and it will be reported in a decimal between -1 and 1. So 0.9 is stronger than 0.8, which is stronger than 0.7. -0.5 is stronger than 0.4, is stronger than 0.2, etc. It just has to do with the number, the magnitude of the number. Okay, so going forward, please do the practice problems and the SPSS project. Please take the quiz before Sunday night at 11:59 p.m. and please do the discussion posting.